The long-sought background of gravitational waves has been discovered. Researchers working in the NanoGrav, North American Nanohertz Observatory for Gravitational Waves project have announced the discovery of the long-sought background of the gravitational wave. The low-frequency vibration of space-time. The likely source of the new discovery is the combined signal from multiple pairs of supermassive black holes. Gravitational waves were first mentioned by Albert Einstein in his General Theory of Relativity, published in 1916. He predicted that the waves emitted by objects with huge masses moving at high speeds propagate through space-time, causing its deformations, a bit like waves on the surface of water. But the first detection of gravitational waves came 99 years later. They were registered in September 2015. But the information was released only after a thorough analysis of the data, in February 2016. The first detections of gravitational waves were made with the LIGO and Virgo ground-based detectors. They concerned the collision of two black holes, but in the following years, waves from the collision of neutron stars were discovered. Astronomers estimate that the events that should trigger gravitational waves throughout the cosmos are numerous and occur relatively often. This means that such waves are constantly creating ripples in space-time, and it is these waves that make up the so-called ripples. Gravitational waves background. Now, several teams of scientists have reported the discovery of low-frequency ripples in space-time, the so-called nanohertz gravitational waves. The discovery was made by tracking the change in the distance between Earth and pulsars in our galactic neighborhood. This showed how the space between the two objects is stretched and compressed by passing ripples in space-time. For the past 15 years, we've been on a mission to find the hum of gravitational waves reverberating throughout the universe and washing our galaxy to warp space-time in measurable ways, says astrophysicist Stephen Taylor of Vanderbilt University, leader of the NanoGrav team. We are happy to announce that our hard work has paid off and we have exciting evidence for this background of gravitational waves. Pulsars are extremely dense neutron stars. They owe their name to the beams of radio waves they emit from their magnetic poles. These beams travel through space in a beacon-like manner. Some spin hundreds of times a second, others even more often. Because pulsars spin with such frenetic speed and regularity, Astronomers can use them as the cosmic equivalent of atomic clocks. Such precise timing helps scientists study the nature of space-time and measure the masses of stellar objects. The first detection of gravitational waves came from the collision and merger of two star-sized black holes. The most likely source of the latest discovery is the combined signal from many pairs of much larger black holes, millions or even billions more massive than our Sun. The wavelengths discovered are thousands of times stronger and longer than those found in 2015, and span tens of light years. In turn, the ripples detected since 2015 are only tens or hundreds of kilometers long. You could say that the Earth is vibrating because of the gravitational waves that sweep across our galaxy, says Scott Ransom, an astrophysicist at the U.S. National Radio Astronomy Observatory who is also involved in the work of nanograv. The astronomer noted that both he and other research teams are not entirely sure of the discoveries. Each group saw clues to the expected gravitational wave signature, but no statistical certainty to indicate a discovery. Scientists talk about discovery when the sigma value is 5 or more. Sigma is a measure of statistical certainty. Sigma 5 means that the probability that this is some random event, fluctuation, disturbance, and not a true observation is 1 in 3,500,000. Researchers reporting new discoveries have reported detections of between 3.5 and 4 sigma, indicating over 99% detection rates. Sure that the signal is real. The researchers will now combine their data to see if they can reach the 5 sigma threshold together. If confirmed, we'll have 20 years of work to study this new background, says Monica Kolpe of the University of Milan Bicocca. It will force an army of astrophysicists to work, he adds. 3 teams of scientists reported similar results based on an analysis of decades of data on pulsar activity. These are the North American Nanograv Group, the European Pulsar Timing Array, with the participation of astronomers from India, and the Parkes Pulsar Timing Array in Australia. A 4th group from China, the Chinese Pulsar Timing Array, claims to have found a similar signal based on only 3 years of data, thanks to FAST's exceptional sensitivity. Nanograv's results have been published in 5 papers in the astrophysical journal Letters. The results of the European and Indian teams' research will be published in Astronomy and Astrophysics. The Australian team sent their research to the astrophysical journal Letters and Publications of the Astronomical Society of Australia. In turn, the Chinese published work in Research in Astronomy and Astrophysics. Each group was based on a slightly different set of data. Nanograv has monitored the most pulsars. In turn, the European-Indian team analyzed the longest collected data set, and the Australian team was the only one to observe pulsars in the southern sky. We are sure of the result because we all see the same thing, says Michael Crame of the Adam Mickiewicz Institute for Radio Astronomy. Max Planck. All groups used sensitive radio telescopes to monitor millisecond pulsars. Every time a pulsar spins around its axis, its radio beam travels towards Earth and beyond. These are emissions at regular intervals. Millisecond pulsars rotate the fastest, up to several hundred times per second. We can use them basically as clocks. Slight variations in the arrival time of the signals from the pulsar could mean that the space between the star and Earth has been altered by the passage of a gravitational wave, says Andrew zWIcQ of the Australia Telescope National Facility in Sydney. Conclusions drawn from the study of a single pulsar would not be reliable enough. So each team monitored dozens of these stars. In addition, the researchers had to rule out many signals potentially interfering with the observed sources. Radio interference from terrestrial and satellite technology. Scattering of radio beams from the pulsar by surrounding gas clouds, and small random changes in the rotation of the pulsars themselves. The LIGO and Virgo detectors are sensitive to millisecond waves produced by single mergers of black holes or neutron stars tens of times more massive than the Sun. The results obtained by synchronizing the pulsar signals instead represent multiple waves, each years or decades long, overlapping in cumulative background noise. Each wave is generated by a pair of supermassive black holes somewhere in the universe whose host galaxies likely collided and merged. To imagine that the universe is a roaring ocean of space stretching and squeezing is unbelievable. Supermassive black holes are cosmic behemoths at the heart of galaxies that feed on gas and interfere with star formation. I look forward to a future where our pulsar observations will reveal the intricate map of gravitational waves emanating from pairs of supermassive black holes. We should see the background noise of the universe with specific hotspots, of gravitational waves from particular pairs of supermassive black holes lying in galaxies that we can identify, explains Daniel Reardon of Swinburne University in Australia.